Okay, I'm going to move on to the next one. Yeah, I'll move on to these other exercises. Okay, you sample 100 bottles of detergent brand A and find that on average each bottle will be sufficient for 57 wash loads. You know that the standard deviation for the entire population of 100,000 bottles is 5 loads per bottle. How do you know that? I made it up. You really would never know that, right? Where's the only place that you actually have a measure of a true population? The census, right? We discussed that, right? Yeah, because they actually do a count. Okay, so let's take a look at this. I sample 100 bottles of detergent, found that an average okay. So you take a sample of 100 bottles of detergent. Is 57? You find that on average, those 100 bottles, 57 wash loads. Is 57 mu or x bar? It's x bar, right? It's the statistical. It's the average of a sample, not the population. Right, right. Is that a parameter? No, the 57. In other words, you sample 100 bottles of detergent and find that on average each bottle is good for 57 washing loads, right? So you have an average for those 100 randomly sampled bottles. That's a sample average, X bar, right? Okay. Standard deviation for the entire production of bottles is 5 loads per bottle. Is that a sigma or SD? Which one is it? Sigma, right? You see a sigma because I said it's for the entire production line, right? It's the entire population of bottles. And mu is a parameter. Mu and sigma are parameters, and X bar and SD or standard deviation are statistics. Okay, okay, and we got that for a second. Okay, okay. Now I'm going to give. Now we discussed when we talked about. Let me go back here. That's the pot. That's okay. Let me go back one more. Okay, our first look at this with that first problem, we discussed the mean of the entire population was 200. The standard deviation for the entire population was 9, right? Then we went over to taking a look at the dynamics of taking repeated samples from that same population. And we call the mean, we expect the mean to be 200 again, because we're taking repeated samples, half time to be above that, half time below that. But we have a new standard deviation. This standard deviation is not the standard deviation of the population, right? We don't know that. But we do know that we can approximate it based on the standard deviation of the population. This standard deviation is sigma over the square root of n. To make sure that we don't mix it up with the standard deviation of the population, which was 25, which was 20 in this case, and this standard deviation for the samples is 4 because we divided it by the square root of the sample size. To make sure that we don't mix it up, we're going to give it a new name. We're going to call it the standard error of the sample means. Okay, so from now on, when we talk about the standard deviation of the population, we'll talk about it as sigma or standard deviation. When we talk about the standard deviation of the sample means, we're going to call it standard error. Yes? I'm sorry, say again? So does that mean that question you said is 5 sigma for the standard error? Yeah, absolutely. Right. And in fact, it is sigma, which is the population standard deviation. Okay, so let's take a look at this. Calculate the standard error for repeated samples of size 100 from this population. Okay, all right. So I think the mean we got there. What was the mean that we got for this 100 bottles? 57. Okay, so the mean is 57. And what's our standard error? It's equal to the sigma over the square root of n. Right? What is that equal to? It's equal to, let's see what we got here. How quickly I forget. Okay, you know that the standard deviation for the entire population is 5, right? So that's 5 divided by the square root of the sample size, which is 100. So what's the standard error? It's equal to 5 over 10, or 1/2. Okay, everybody okay with that so far? Let me just check online, see if I got some questions. You guys are okay online? I don't see too many questions, but so, okay, good. All right, so now let's see if we have any questions that they want us to answer based on this. Okay, calculate standard error, we just did that. Calculate 95, oh, Jesus, we're getting at the confidence interval. I'm not, let's ignore the word confidence interval. I think we must have combined this last semester. Okay, I don't want to talk about, I'm going to ask you, instead of that, let's forget the word confidence interval. I'm going to ask you, what's the range of numbers that we would expect 95% of the sample means? If we took a sample of size 100, 95% of the time the results would fall within how many standard deviations below and how many standard deviations above? Right? 2. Okay, so 2 standard deviations below and 2 standard deviations above. So in our case, for samples, what is that number going to be? The mean is for all the samples is going to be 57. It's going to be an approximation of the population mean. So what is that number going to be below? It's going to be 2 standard deviations below. And how much is 2 standard deviations? It's 1, right? 2 times 1/2 is 1. So it's going to be 56 and 58. So we would expect, if we took a sample of size 100 from this population, right, we would expect 95% of those samples to fall within 57 and 58, to fall within 2 standard errors below the mean and 2 standard errors above the mean. Right? So if we knew what the so in other words, if we know that the population mean is really 57, which we don't, that's what we would expect. Okay, so let's move on. Take a look. Okay. And let me rephrase this B, because I want to try and avoid the use of the word confidence interval, since we're really going to get into that next week. I get a little bit of a preview. Wouldn't hurt a little bit of a preview, I guess, right? If a company is known to produce a product that washes 95 loads per bottle, right? Can you say, how certain are you that, this is pretty simple one, this is going to be an obvious one. If a company produces a product that they know the population about all their bottles, average of all their bottles, does 95 loads per bottle, can you say that it's really different than the ones that you're testing, that ones you took a sample of 100? Well, yeah, it's way more than this one is, right? In other words, the probability of having getting a mean from this population that's that high is like infinitesimally small. It's way out here, right? 95% would be in here. 99.7 would be like 57, like 55.5 to 58.5. So it's so different that we would never expect to get an average from a sample that big. Okay, let's leave it at that. Okay, suppose we want to know the true probability of the random selection of Americans of the environment. Okay, that's, I don't want to do that one. Levi, did you talk about proportions at all? I think it can come up, right? You talk tonight about proportions? Okay. All right, good. Okay. So, let's take a look at the situation where we're looking at proportions. We want to estimate the true proportions of Americans that are willing to accept the cut and living standards to help the environment. Okay, it's a lot better in the 70s than it is now. Let me tell you, I was just reading a survey somewhere that very few millennials are willing to compromise like their salaries for improved environment. So anyway, that's based on the survey there. So in this survey, Out of 1,381 respondents, 496 said that they were willing, very willing, or fairly willing to take a reduction in salary. So what's the proportion? What's a proportion of people that are willing to take a cut in salary? I'll get those numbers again. 1,381 is our sample size, right? The number that is willing to take a cut is 496. So that leaves the remainder are not willing to take a cut in salary. So what's P? What's the probability of picking an individual in this population, or what proportion of the population is willing to take a salary cut? 496 divided by 1,381. Okay, so what does that come out to? You guys want to do the calculation for me, or should I get my calculator out? 33%? 36%? Okay, 0.36. Okay, now, okay. Okay, let's see. Is it a random sample of Americans? I don't think I gave you a, okay. So now, you guys remember how we calculated the standard error for, or standard deviation for proportions? Right? We took, it was the square root of n times p times q. Right? You remember the binomial distribution? Yes. Well, this time we're going to do something a little bit different. That's a normal approximation to the binomial distribution. This time it's going to be our standard deviation, or standard error, is going to be equal to the square root of p times 1 minus p over n. It's basically the same thing, right? And it's, in a sense, it's really the same thing. Okay, let's just use the formula for now, and we'll take a look at how it works out. Okay, so now, what is this number going to come out to? P, right? I'm going to call it P cap, because it's kind of like an average, like our X bar, right? P cap is 0.36. That's what we think is the proportion of people that that in our sample were willing to take a pay cut. Okay, so now we need to know what's the variability here, right? And the variability is going to be based on the sample size and the proportion. Okay, so our standard error is going to be equal to the square root of 0.36 times 0.64 over sample size. What was the sample size? Right, it was 1381. Just like working with a numerical variable, right? It's based on the bigger the sample sizes, the smaller the standard error is going to be. So what number do we get here? Divided by 1381. Okay, and I'm going to, oh, I must have made a mistake there. Oh, no, I didn't make a mistake there. 0.36 times, you're going to come up with a pretty small number, because when you take the square root of it, it's going to be a bigger number, because it's a number smaller than 1, divided by 1381. That, and take the square root of that, and it comes out to 0.012, 0.013. Yes, square root of the whole thing. Yep. Okay, it comes out to 0.013. Well, that's our standard error. So if I were going to take repeated samples of size 1381 from this population, I'm predicting that on average, we're going to get a result of 0.36, right? But we're going to get 95% of the outcomes, maybe, and this is kind of a little bit of a, when we talk about confidence interval next week, we're gonna take another look at this. We don't really know what the population mean is, right? All we know is what we think the population mean is based on our sample. So I'm kind of twisting this a little bit to, say to myself, I'm going to assume that that's what the population mean is for right now. For next week, we're going to see that that's not really true. This is really an estimate of the population mean. So we're going to use these numbers a little bit differently next week when we talk about confidence intervals. But for right now, based on what our standard error is for this proportion and for this sample size, we would expect that 95 or we would expect that 68%, if we took repeated samples from this population, that 68% of the outcomes would be between 0.36 minus 0.013, right, which is roughly 0.373, and plus 0.36 minus 0.013, okay, or about 35%. So we would expect 95% of the outcomes to be somewhere between 2 times that, right? Yes. Right. We use a square root of p times 1 minus p over n. Okay, for the variability, for the standard error, for repeated samples of that size. This is I'm kind of giving you like a kind of a white lie here on how this is really used, right? Because I don't want to cross over too much into what we're going to be doing next week right now. Okay, to give you a little bit of a preview, really what's going on is we don't know what P is, what true P is. We have no idea what it is, right? All we know is what we got from our sample. That's always going to be true. We're never going to know what mu is. We're never going to know what the true proportion for Americans, all Americans, is. All we know is the X bar that we calculate from our sample and the P cap that we calculate from our sample. Yes. Somebody's asking me a question? Okay. Oh, okay. For our purposes, I'm using 2 just to save time, so I don't have to go back and forth to the Z table, right? But yeah, we should get to the point where we're going to use the Z table or the function in Excel all the time. That we're not going to depend on the empirical formula anymore, right? But for our purposes, right now, I'm going to use 2. But I think as we move forward, we'll be just sticking to the Z table at some point. Okay, I'm just doing it as a convenience, just like I'm rounding off these numbers quite a bit. Yes. When you're doing something that involves a choice that has 2 outcomes, like for instance, will you take a salary cut? Will you not take a salary cut? Right? You're never going to have a mean. You're going to have a proportion for that, right? There's going to be a lot of things where the data is going to be a proportion rather than, a scale, a numerical scale, right? In this case, that doesn't mean that we can't look at it as when we're taking repeated samples and we're finding like we take a sample of 100 people, finding that in the first sample, 42% of the people are voting Hillary Clinton. In the second sample, 39%, second and third. We can still look at that as a normal distribution. The true proportion might be 47%, right? But we're rarely going to get exactly the right proportion for the whole population. Half the time we're going to be under 47%, half the time we're going to be over. It's going to be normally distributed. We're going to be off by a lot less frequently the further and further that we get from that. Now let's take a look at this. If this is what this is going to look like, whether it's a mean or a proportion, if this is if all these outcomes are going to be normally distributed, we don't really ever know what mu is. We don't really ever know what p is, right? So the way we're going to wind up using this is that when we take a sample and the portion comes out to be 0.36, we're going to use the variability that we have here and say to ourselves, well, if I assume for the moment that the true population is 36% of the population is going to be willing to give up a salary, and the outcomes might be 95%. For 95% of the outcomes would be between 2 standard deviations below and 2 standard deviations above. I don't really know that that's really the true population. That just happens to be what I got in that one sample that I took. I'm never really going to take thousands of samples. I'm only going to take one sample. So we're doing this only because we're trying to understand the way samples work, right? So now, what I'm going to say instead now is, I don't know what the true proportion is, but if I for a moment assume that that's a pretty good estimate of it, well, I'm going to use this standard deviation, this variability that I'm predicting. I'm going to use this to predict how far off I might be from the real population. So next week, when we take a closer look at this, we're actually going to be starting from the proportion or the mean that we got, say it was 200, right? We're going to be starting from that mean or from that proportion, and we're going to be using the standard deviation as a tool to tell us how likely are we that we're close to the mean, okay? And instead of like worrying about what the actual range of what the actual mean is, or how well this predicts the actual mean, we're going to say, well, the variability tells me that I'm within, that if I go 2 standard deviations to the left and 2 standard deviations to the right, well, that represents 95% of the outcomes if I'm right. Maybe I can use that another way. Maybe I can use that as a range. So for instance, I might be able to use that as a range to say that I'm 95% certain that the true population mean falls between 190 and 210, or that the true proportion falls between 2 standard deviations on the other side of this, that the true proportion, P, is somewhere, we're 95% sure that it's going to fall between, say, 34 and 38. I'm going to use this as a mechanism for predicting where the true mean is at a certain level of certainty, right? And I could have said that I'm willing to be only 68% sure of the range of capturing the true mean within that range, in which case I would only go 1 standard deviation above and 1 standard deviation below. If I want to be 99% sure, I might go 3 standard deviations below and 3 standard deviations above. And what would happen? What does that mean? That as you make your range wider, you're more confident that the true population mean is going to be within that range. Okay? So next week, when we talk about the confidence interval, this idea of standard error and how these sample results are distributed are going to be a useful tool for us to help us predict, based on one sample, what the true population mean is, but not as a specific number, because we're never going to know what that specific number is, but as a range that we have a certain level of confidence that it's really in that range. Well, what good does that do? Well, if you can say that I'm 95% sure that American cholesterol levels are between 180 and 200, and I'm 95% sure that French cholesterol levels are between 210 and 240, well, you can say to yourself, well, gee, there seems to be very little likelihood that there's overlap between these, between these two. That is very unlikely that the difference in the mean that I found for our sample of Americans, our sample for Frenchmen, is due to chance only, right? Where if I had told you that the range for Americans was 190 to 200, and the range for Frenchmen was 195 to 205, it's a lot harder to say that they're really different, because we could have easily, the real population mean for Americans could easily be 196, and for a Frenchman could be 195. So, we could have the opposite result, right? So we can use this as a tool to understand what the probability of two different groups being the same or different, for how well we're predicting the actual mean in a population, and so on. Okay, let me see if we got a couple other examples I can use. I unfortunately got ahead of us with some of these examples. What the hell? Let's go ahead and do this. Let's do number 3, and let's go ahead and take a leap and calculate a confidence interval. Except I'm not going to calculate a real confidence interval. I'm going to use the empirical formula for our confidence interval. Next, we're going to calculate real confidence intervals. High efficiency washers, the result, how many loads are full out? The results in number of loads washed. We don't really care what this whole thing is telling us. All we really care about is that its sample size is 10, right? Is it really 10 people there? 4 or 5. There's really 10 people there, 10 results there. The sample size is 10. These are the results of that sample. Okay, and let's calculate what the mean of that sample is. Okay, let's. I'm going to open up Excel. Going to increase this to 250. Okay, let's see. Let me get this out of the way. Okay, so 87, 88, 103, 98, 94, 99, 89, 91, 87, 91. Okay, so my mean is 92.7. Okay, so now what do I need to know to calculate a standard error? I need the standard deviation of the population. I need sigma, don't I? Am I given sigma in here? It doesn't look like I'm given sigma in here, right? So, but I'm going to need sigma. Now I'm going to, I go way ahead of us on this. Okay, I'm gonna calculate standard deviation here of these 10 numbers, just because I want to get a decent number. Okay, I'm going to say 6. I'm going to tell you that sigma is equal to 6. Okay, so now let me ask you this. This is the mean is equal to 92.7. If I didn't know the population mean sigma, in real life, I'm never going to know it. Just like population, I'm not going to know the population sigma, right? Where would be a good place for me to estimate the population standard deviation? Population, from the sample I took, right? Just like the mean estimated the middle of the distribution, the sample distribution can estimate what sigma is because it's all individuals within that population also. Just like, remember when he took a sample size of one person, that the variability was very similar to the variability of the population when he took a sample size of 1. Look, the distribution was almost exactly the same. So you can use it. It introduces a big error. So we're not going to do that now. We're going to assume I told you what sigma was, at least for the next 2 weeks anyway, next week or 2, right? So sigma is equal to 6. But when we work with samples, we're actually going to use the sample to estimate sigma as well. But in this case, we're going to play by the rules because we need to know sigma to actually calculate the standard error. Okay, so now sigma is equal to 6. So what is my standard error? What is the distribution of my repeated samples? It's equal to 6 divided by the square root of what? Sample size, 10. Wonder if that'll work. Let's see if it'll work. Yeah, it worked. Okay, so what is the standard error? is equal to 1.89. Okay, so I'm going to call that 2, just to simplify things. Standard error is equal to 2. So if I were to ask you, where would you expect 95% of the sample results to, if we had got lucky and 92.7 was really the mean for this population, where would you expect 95% of the sample results? What would be you expect to be the range of 95% of the sample results? Standard error is 2, right? So I would expect that it would be 2 standard deviations below the mean and 2 standard deviations above the mean. So that would be 92.7 plus 4, right? Which would be 96.7, and 2 standard deviations below, which is 2 times 2 is 4, which would be 88. Am I right? 88.7. Right? That's what I would expect. Only problem with that is that we really don't know that the mean, if the mean is really 92.7, because it's only a sample size of 10, and we're never going to know what the population mean is. So we're going to use this in the coming weeks. We're going to use this differently. We're going to use this range not as the range that we would expect all these samples, the repeated samples. If 92.7 was truly the mean of the population, and 6 was truly the standard deviation for the population, then this would be true. 95% of the time, repeated samples of size 10 would fall in between 88.7 and 96.7. But since we don't really know that, we're going to use this differently. We're going to use this to say that although the mean of this particular sample was 92.7, the variability in the population and the sample size suggests that we're 95% sure that the true population mean is between 88.7 and 96.7. Okay? We don't really know anything about 92.7. That just happened to be the result that we got from this one sample, right? But now we can put a probability, we can put a level of confidence on this range of numbers from 88.7 and 96.7, right? And this is based on what we understand about how samples are distributed, right? So there's a value in that, right? Now we can predict how likely we are that we're correct, right? That the population mean is between these two numbers. And what would I do if I wanted to be 99% sure? Bingo, perfect. I love that you said that, right? You would make it 3 standard deviations above the mean. And what would that mean? That would mean that this would be 98.7 and this would be 86.7. So if you're willing to accept a wider range for your mean, you can have a higher level of certainty. If you make the range narrower, you have a lower level of certainty that you really capture the population mean between those two numbers. Okay, so this is kind of a combination of what we were talking about tonight and what we're going to be, where we're going to be going with this next week. Okay, and let's see. Okay, let me give you one more example. Okay, I'm gonna word out an example. How are you guys doing online? Okay, sounds okay. Okay, let me get my notepad back. Oops, went away somewhere. There it is. Okay. Say we take a sample of 36 Hunter students. We ask them, we ask them what their cumulative average is, and we find that they report their average cum for these students is 3.1, and we happen to know, for whatever reason, that the true standard deviation of all scores for Hunter students is 1.2. Okay, that's the true standard deviation of grades is 1.2. Okay, so now our sample, this would be X bar. That's the result of our sample, right? And so what would our standard error be here? Right? What's the standard error equal to? The population standard deviation over square root of the sample size, right? So what's our standard error? 36 is going to be 6, right? It's going to be, excuse me, it's going to be 1.2 divided by 6 is going to be 0.2. Okay, so that's our standard error. Okay, the population standard deviation is bigger than the sample standard error, the distribution of the samples, right? Because the distribution of these samples of size 36 are going to be narrower than the population distribution. Okay, so now if that's true, let me draw a distribution here. Okay, so the mean is 3.1. Okay, and our standard error is equal to 0.2. Right. So now, two standard deviations below 3.1 is going to be what? 0.4 is going to be 2.7, and two standard deviations above is going to be 3.5. Right. So we have 95% confidence that the real average for all Hunter students is really somewhere between 2.7 and 3.5. Right? If we happen to know that the true population mean was really 3.1, I could have also said that if I took a sample of size 36, 95% of the results would be between 2.7 and 3.5. If I happen to get the mean exactly right, if X bar is equal to mu, I can say that also. But if I don't know mu, then really I have to fall back on this idea of confidence interval. So that white lie I told you before was that I knew that the distribution of all the samples would be 95% would be between 2.7 and 3.5. I really don't know that because I really don't know the population mean. Right? If I knew the population mean, I would know that, right? But I can't tell that without knowing the population mean. So the only way I can really use this legally, and forget about that white lie, is to use it to define a range within a level of certainty that I would expect that I actually captured the population mean. So okay, so let's say, so I'm going to call that a 95% level of certainty. That's the confidence, right? Next week, when we're officially studying the confidence interval, that's going to be our confidence interval. Okay, what would be your 99% confidence interval? Remember what this is 0.2. What's it going to be? 2.5 to 3.7. Right, exactly. That's going to be wider. Right, what's our 90% confidence interval? Uh-oh. Uh-oh. Exactly right. Thank you again. All right, you're on the ball tonight. We need a z-score for 90, right? That's the number of standard deviations that a z-score for 90% would be. We'd have to go to the table, find out what that z-score is, and that's the number of standard deviations. It doesn't have to be a whole number of standard deviations. It can be a fractional number of standard deviations below and above. In fact, for 90%, you have no choice because we don't have an empirical formula for 90%, right? So that's the way that we're going to wind up using this function. Okay. So I think you guys are picking this up pretty well. Yes? Yes? Between these two numbers, yes. Oh, well, 90%. Let's take a look at that. Well, we got a problem there, and that is what I've really been doing when I've been doing this is I've been saying that I'm 95% sure that it's between these two numbers. How did I find those two numbers? I said X bar, the mean, and then I said minus the 2 times the standard error, right? When I said X bar plus 2 times the standard error to get that 95% confidence interval. Another way to write that would just be X bar plus or minus 2 times the standard error, right? And why did I use 2? Because for 2 standard deviations, 95% of the population on either side. So now if I want a 90% confidence interval, I can't use 2. In fact, I shouldn't even really use 2 here because 2 is just an estimate. What is that number really that's 95% on either side? Let me pull up the z-table. Are you close? That's 90%. Is 0.158, but we're going to get to that in a second. For 95%, you just got a little bit ahead of me there. For 95%, if I can get this to come up. Okay, why can't I find it? Okay, there it goes. Okay, for 90%, I'm looking for an area to the left that's 2.5%, right? 2.5% at the bottom, 2.5% at the top. So I'm looking for 2.5% here. So here's 2.5% right here, right? Let me highlight this 2.5% right there. Okay, that's 0.250. And what is that? That's 0.1901234 0.196. 1.96 rather. In other words, really 95% of this distribution is in the middle, right? If I use, instead of 2, 1.96. 2 is just an estimate. So my formula is going to be X bar minus 1.96 and like X bar plus 0.196. So now for a 90% confidence interval, I want to use the range that's going to be 5% down here and 5% up here, so that all I'm capturing in the middle is the middle 90%, right? So what is 5%? Let me go over here and what the z-score is for 5%. Area of 5% would be, here we are right about here, 1.60123, around 6.4. So it's going to be X bar plus or minus 1.64 standard errors above and below the mean. Okay, that's going to be our 90% confidence interval. Right? Yeah, I'm using the z-table in reverse. Exactly right. I'm using the area that I want of the curve, which is 5. The bottom tail is 5%, the top tail is 5%, and then I'm capturing the middle 50% of the outcomes. Right? You still have a chance. In other words, if I'm looking at this range, you still have a chance that the mean is outside of that 5, is beyond the 5% below and 5% above. That's why you're not 100% sure. You're only 90% sure. 5% with 90% confidence interval, 10% of the time you're going to be wrong, right? That's statistics. That's why, you're like saccharin is killing you, then saccharin's okay, and coffee's killing you, and coffee ain't killing you, and so on and so forth. Because most of these studies, they set a level at which they're satisfied that that level of confidence is enough for them to come to a conclusion. Right? This is not physics where you like Newton, like Da Vinci, not Leonardo da Vinci. Is it Da Vinci? Dropped the feather and the ball from the Leaning Tower of Pisa, and it comes down. Is that Galileo? That's Galileo, right? Right. So it's not physics where you get the same outcome every time and it's completely predictable, right? Not quantum physics. That's a different thing. But I mean, Newtonian physics, perfectly predictable, right? So now this is like we're dealing with living systems, things we can't predict, things that are very variable, and so on and so forth. So we can't have 100% certainty. So 95% certainty is pretty good for most surveys. So when you have 95% certainty, you got a 1 in 20 chance of being wrong. So things do go wrong. Now, I'll give you an example. When I went to college 100,000 years ago, a lot of people were into paranormal research and all sorts of weird crap. There was this one group that did studies with these things called tubiflex worms, right? Nematodes or tubiflex worms. They're tiny little worms, right? That you get they use them to feed fish, and do a whole bunch of other things. Well, apparently they could train these worms, put food in their environment, and train them to either turn towards the light or turn away from the light. So that, they put the worm in the environment and it would turn towards the light or turn away from the light, and you would get food. So they could train. It was a behavioral response. They could train this it's respondent condition. They could train it to do that. So the worms would learn to do that. So most of the time they would get it right after they've learned it, right? So they took the worms that they trained and they put them into a blender and ground them up and fed them to other worms, right? And in this study that they did, they claimed that their results showed that the worms that they fed worms randomly to naive worms. Some of the naive worms got the trained worms, some of them got untrained worms, and they claimed that the ones that ate the trained worms learned in a shorter time than the ones that ate the untrained worms. That it was actually by consuming these other worms that were able to, learn more quickly, right? Well, turns out, and they had all this statistical evidence to show this was true, right? And they were certain. They managed to get published somewhere, but it was retracted because what happens when you publish a study? Somebody else tries to replicate it, right? And when they can't replicate it, then they say, "Oh, you were all wrong." They pull the publication and so on and so forth. These guys were so adamant about this that they started their own journal called the Worm Runners Journal, and they published all the articles that nobody got, no other legitimate journal with all these paranormal things and stuff like that. And they disappeared. They were around for about 5 or 6 years. If you got, it's like we're talking about a period before the internet. So you might find material about this. You might not find material about it. Trust me, this really happened. Right? But that's what happens. That's what we're in the business of not necessarily knowing perfectly, but at least understanding what we don't know. That's what this is really all about. Okay? Okay, guys. Good night, guys. Good night, guys online. Yeah, I see that. Let's see. Oh, let's see if I can answer it before everybody goes away.